Hello everyone, welcome to this session and welcome to Physics Revolution. After long, I am coming back with a video. And what I'm going to discuss today is a A-level topic, and it's a very interesting topic. Basically, it is the Einstein's photoelectric equation. This forms a part of quantum mechanics. It's a part of quantum mechanics, and it's a very nice theorem which basically shows you the conservation of energy taking place, and it is for this particular topic, it is for this particular equation Albert Einstein got his Nobel Prize too. We must be thinking that he got his Nobel Prize for relativity and E is equal to mc square. No, but actually he got his Nobel Prize for the work in photoelectric effect, and here I'm going to discuss the equation that got him that prize. And I'm going to make this in a very simple way. You are going to understand this in a very simple way. Just follow with me. Let us get into the topic. Right. As you can see here, Einstein's photoelectric equation. To begin with, you should understand what is this photoelectric effect. Okay, so basically it's a part of photoelectric effect. Okay, it's a part of photoelectric effect. Now, those who do not know, photoelectric effect is a phenomenon where I'm going to send a appropriate light ray on a metal. Remember, here I am going to deal with a metal. I'm going to send a light ray of appropriate frequency on the metal, and that metal is going to eject an electron outside. Now you might ask me, where is this electron coming from? These are the free electrons which are present in the conductor. Metal is a conductor, you know that, right? Metal is a conductor. Now there are free electrons in this conductor who are residing on the surface of the metal. There are electrons which are bounded electron. These bounded electrons are basically in the atom. We all know that there are electrons which are bounded to the atom, but these electrons are not free. But in a metal, you have free electrons, which are the reason why they are conducting in nature. These electrons carry the current basically. Okay. Now, when I'm sending a light ray of appropriate frequency, it is going to eject the electron outside the metal. That means that the electron is going to gain some energy from that, light ray, and it's going to come outside. This particular effect is known as photoelectric effect. And photoelectric effect was a phenomenon which actually also said that light is a particle, because only a particle can kick out another particle. A wave cannot kick out a particle. Only a particle can kick out a particle. This is also one of the fundamental things which tells that light is a particle. And we all know that it is photon. Right now we know that light is photon. So now, let's see how this Albert Einstein, one of the genius scientists, came to the conclusion and came to the equation that we are talking about. Now, here he used a very simple concept, and that is known as conservation of energy. If you have been studying physics from quite few time, you will be knowing about conservation of energy, which says that energy cannot be created nor be destroyed. Energy cannot be created, cannot be destroyed, but can go from one form to another form. It can go from one form to another form. And here also I'm going to see the change in the form basically. And let's see how it happens. Okay. We know that light carries an energy. Okay. Light carries an energy, and that energy is equal to E is equal to hf. Basically, h is the Planck's constant and f is the frequency of light. H is the Planck constant and f is the frequency of light. This is the energy carried by the light. Now, these electrons, these electrons who are residing on the surface of the metal, you see here, these electrons who are residing on the surface of the metal, they have a requirement. That means if they get X amount of energy, they will leave the surface. Again, I'm telling you, what do these electrons want? They want X amount of energy. If they get that X amount of energy, they will leave the surface, right? Now, who is getting this energy for them? It's none other than the light itself. Okay, so I told you there is a X amount of minimum energy that is required, or else electron will not come out of that point. Electron will not come out of that position. That energy is called work function. Okay, that minimum energy required for the electron to be ejected outside the metal is known as work function, and is usually sorry, it is usually represented by phi, a Greek letter phi. Alright, it's represented by a Greek letter phi. Okay, now, okay, I got this. Not only that, now let's say that a light falls, okay? Let's say that a light beautifully falls on an electron and the electron gains the energy. Now, it's a mandatory thing that this energy should be greater than the work function, because if it is not greater than the work function, it is not going to eject out. If it is less than the work function, then electron is not going to come out. Electron is not going to come out. The electron has to, the light which is coming on the electron, the light which is falling on the electron need to have a greater energy than the work function, either equal or greater. So let's say if electron is this light which is falling, the light which is falling is having an energy greater than the work function. So what is going to happen? This electron is going to happily leave this place and come out of the metal, because the light is used to overcome the work function and the electron comes out of the metal. Now after electron comes out of the metal, what does it do? It has to run, it has to move with the velocity, right? It has to move with a velocity. Now in order to get a velocity, you should have a kinetic energy. Kinetic energy is the energy associated with the moving object with a velocity. So if the electron is moving away with some velocity, that means this electron has a kinetic energy. Now you look here clearly. To remove the electron, you require work function. To run the electron, you require kinetic energy. Now who is giving all this energy? It is none other than the energy of the light. So look here. Energy of the light is the incoming energy. It is the incoming energy. And where is it coming from? It is coming from basically the light. That is your h mu, hf value, h into frequency. Okay, now what are the energy that is being used? One is work function that is being used, and other is a kinetic energy that is used by the electron. So these two energy are used by the electron. One to come out of the metal, other to run away from the metal. So according to conservation of energy, the energy incoming should be the energy outgoing, right? So it is very clearly said that the incoming energy is equal to work function plus kinetic energy. Now, to show this equation much more appropriately, I have h into f equal to work function, okay, work function plus half mv square. Now you all know by now that kinetic energy is half mv square, right? You all know that kinetic energy is half mv square, and mu, what is this? Pi is the work function here, right? This is known as Einstein's photoelectric equation, right? So it is just a simple conservation of energy in action. This is the famous equation for Albert Einstein got the Nobel Prize. Okay, now talking about the work function, now you might ask me, is work function same for every metal? No, different metals have different work function value. Copper has different work function value, aluminium has different work function value, iron has different work function value. Every metal has a different work function value. So a work function is associated with the metal. It depends on the metal type, what type of metal we have. Different metals have different work function value. So if you want to eject an electron from metal X, you need to put the work function of metal X, then only it is going to come out. It makes sense? I hope it makes sense for you. Okay, then only it comes out. Now same way, so now let me so I have work function, right? Work function is also energy. Now what is the minimum frequency that is required to eject? To find the minimum frequency, it is work function is equal to hf naught. Now here f naught is known as threshold frequency. Okay, it's called threshold frequency. Threshold frequency is the minimum frequency required to eject the electron outside the metal. Okay, now one more question you might have: what if my energy is equal to work function? What if my energy is equal to work function? What is going to happen? Now see, it's a very interesting case. If energy is equal to work function, the electron is going to come out, but it does not have kinetic energy. It does not have kinetic energy. Since it does not have kinetic energy, it is going to be captured back to the metal. Understood? See here, when E is equal to E is equal to phi, your kinetic energy is equal to 0. Kinetic energy 0 means velocity is 0. When velocity is 0, this electron is unable to go away and hence will be captured back to the metal surface itself. So this is the case that happens when Ke is equal to 0, when the incoming energy is equal to threshold frequency. That's why it is said that for a proper photoelectric effect, your incoming energy E should be very much greater than threshold frequency in order for the electron to go away from the metal. Alright, in order for the electron to go away from the metal. So this is known as Einstein's photoelectric equation. So I hope I have made this concept much more simple to you, and there are different ways of doing this. If you want me to make things easy for you, make things simple for you, I will be I will be ready to make videos for CBSE, IBDP or AES level videos. You can just put it in the comments which section and which part of the physics class you want me to do. Just put it in the comments. I will do that. Depending on the comments, I will make the video and make the concept very much more simpler for you. So I hope you enjoyed this video. So we will see in the next video, upcoming video. Until then, adios.